Google's Willow chip is touted as not just another technology breakthrough, but an evolution in the way we solve some of the world's toughest challenges.
In December 2024, Google's quantum computing team paused operations on their Willow processor, but not because it failed. It was because it succeeded in a way their own models couldn't fully explain. The system didn't just do what it was designed to do, it went beyond it, creating a gap in understanding big enough to force the team to stop and reassess. What it revealed has raised serious questions ever since. Do you think this breakthrough was truly impossible? Yes or no? Let us know in the comments. What quantum computing actually is. Before the specific discovery that produced the pause can be understood in its proper weight, the context of what quantum computing is and what the Willow processor was built to accomplish needs to be clear, because the significance of what happened in December 2024 is only visible against that background. Classical computing, the architecture underlying every device from a smartphone to the most powerful supercomputer currently operating, processes information using bits. Each bit is a switch in one of two positions, 0 or 1. Off or on, representing the smallest possible unit of information in a binary system. Every operation a classical computer performs, every calculation, every search, every piece of software running on any device anywhere in the world reduces at its foundation to a series of operations on bits. The power of classical computing comes from performing those operations at extraordinary speed and at enormous scale. Modern processors execute billions of operations per second. Distributed computing systems connect thousands of processors to work on problems simultaneously. The achievement is genuinely remarkable, and the practical consequences have been transformative. But the architecture has a ceiling that becomes relevant for a specific class of problem. Problems involving very large numbers of interacting variables, where the number of possible combinations of those variables grows exponentially rather than linearly with the size of the problem, hit a wall with classical computing, because the number of operations required to explore the full solution space grows faster than any classical system can process, regardless of how fast the processors are or how many of them are connected. Drug discovery involves understanding how a candidate molecule interacts with specific proteins in the human body, where the quantum mechanical behavior of the atoms involved determines whether the interaction produces the desired effect. The number of possible configurations to evaluate is enormous, and classical simulation of quantum systems is inherently limited because the quantum behavior that determines the outcome cannot be fully represented in a binary system. Climate modeling involves so many interacting variables at so many scales simultaneously that the simplified models, classical computers can lose accuracy in ways that matter for the predictions they produce. Material science, logistics optimization, and cryptography all contain problems whose solution space is large enough to defeat classical approaches regardless of the computing power applied to them. Quantum computing addresses this class of problem by using quantum mechanics to process information differently. A qubit can exist in superposition, effectively both 0 and 1 until measured, enabling simultaneous exploration of many states. Entanglement links qubits, so their combined states scale exponentially. Google built Willow to push this frontier, and what it observed went beyond expectations that researchers had not anticipated. The breakthrough that produced the pause. The specific achievement that Google announced in December 2024 with the Willow processor addressed a problem that had long been the central obstacle to practical quantum computing: error correction at scale. Qubits are extraordinarily fragile. Their quantum states, the superpositions and entanglements that give quantum computers their power, are easily disrupted by interaction with the environment. A stray photon, a temperature fluctuation, or even a minor vibration can collapse a qubit's state and introduce errors. As systems grow larger, the number of potential error sources increases, making reliability a major challenge. For decades, the prevailing expectation in quantum computing research was that scaling up qubits would worsen this problem. More qubits meant more complexity, more environmental exposure, and more accumulated errors. The theoretical outlook suggested a limit. Beyond a certain point, adding qubits would degrade performance rather than improve it, preventing large-scale, practical quantum systems. Willow reversed that expectation. As the number of qubits increased, the overall error rate decreased instead of rising. In other words, scaling improved stability rather than undermining it. This marked the achievement of below-threshold error correction, a long-sought milestone where adding more qubits enhances computational accuracy instead of reducing it. This result alone represented a major breakthrough. It demonstrated that quantum systems could be scaled in a way that supports reliable computation, potentially moving the field from experimental prototypes toward practical applications. It validated decades of theoretical work and engineering efforts aimed at making quantum computing viable. However, the most surprising aspect of Willow's performance was not the success of error correction itself. The pause came from what emerged alongside it. As the system operated with higher coherence and stability, it began producing solutions through pathways the research team had not explicitly programmed. These were not simple optimizations of known algorithms or faster versions of existing methods. Instead, the system appeared to discover alternative approaches to solving problems, approaches that were not anticipated by the team's models or designs. The outcomes were valid, but the processes behind them were not immediately understood. An analogy often used is that of an athlete winning a race using a completely unfamiliar technique, one that coaches did not teach and cannot yet explain. The performance is measurable and real, but the underlying method remains unclear. This unexpected behavior did not contradict quantum theory, but it highlighted gaps in understanding how large, coherent quantum systems behave in practice. It suggested that once error correction enables sufficient scale, new dynamics may emerge that are difficult to predict using existing frameworks, making further investigation essential. The unsettling discovery. The specific quality of what the Willow team observed when the system began producing unexpected solution pathways is important to characterize precisely, because both overclaiming and underclaiming about what it represents would miss what makes it genuinely significant. The system was not exhibiting anything that could be described as consciousness or awareness in any meaningful sense. It was not communicating. It was not expressing goals or preferences. What it was doing was producing solutions through computational processes that the team could verify as correct but could not trace back to the algorithms and instructions they had programmed into the system. The solutions emerged from the computational substrate rather than following the pathways that the programming specified, and the emergence could not be fully explained by the theoretical framework the team had been working within. This is a specific and well-defined kind of scientific problem. When a system you have built behaves in a way that your model of that system predicts, your model is confirmed. When a system you have built behaves in a way that your model does not predict, your model needs revision. The revision required by Willow's unexpected behavior was not a minor adjustment. It concerned the fundamental question of how quantum systems at scale process and organize information, a question that the team's research had been designed to answer, and that the answer they found was different from what the question had led them to expect. Dr. Nevin's public statements in the weeks following the December announcement were careful in a way that reflected the specific nature of what the team was dealing with. He did not claim that Willow had done something miraculous or that it had exhibited anything beyond physical computational processes. He did claim that the system's behavior at scale had exceeded the team's full theoretical understanding of why it was working the way it was working, and that this gap between observed behavior and theoretical explanation was significant enough to require a deliberate adjustment of the experimental program before proceeding. The pause was not a shutdown. The system was not powered down. The research program was not canceled. What changed was the experimental protocol, the specific questions the team was asking, the measurements they were taking, and the pace at which they were proceeding. The adjustment was motivated by intellectual honesty about the gap between what the system was doing and what the team understood about why it was doing it, and by the scientific responsibility to close that gap through careful investigation rather than to proceed without understanding the mechanism producing the results. The difference between a powerful tool and a tool that surprises you is the difference between a hammer and something you picked up that turned out to have capabilities you did not design into it. The surprise itself is not dangerous, but it is information. It tells you that your model of what you are holding is incomplete, and that proceeding without revising the model means proceeding without understanding what you are doing. The Willow team's decision to pause was the decision that a genuinely scientifically rigorous team makes when this situation arises. The physics behind the mystery. The specific mechanism that produced Willow's unexpected behavior sits at an intersection of quantum physics that has been theoretically understood for decades, but has never been observed at the scale Willow made possible. Quantum mechanics contains a fundamental tension between measurement and state. A quantum system in superposition exists in multiple states simultaneously until it is measured, at which point the measurement collapses the quantum state to a definite value. This is the core of the measurement problem: why quantum systems behave as if they hold multiple states until observation, after which they behave classically. It is also the core engineering challenge in quantum computing. To extract a result from a quantum computation, the system must be measured. But measurement destroys the very quantum properties that make the computation powerful. This creates a paradox. The system must remain unmeasured to compute effectively, yet must be measured to produce a usable answer. Managing this tension is central to building practical quantum machines. Quantum error correction addresses this through indirect measurement. Instead of observing the qubits directly, the system measures relationships between qubits. These relationships reveal whether errors have occurred without exposing the underlying quantum information. In this way, the computation remains intact while errors are detected and corrected. One of the most important frameworks for this is the surface code. In this approach, quantum information is distributed across many physical qubits arranged in structured patterns. By measuring how neighboring qubits relate to each other, the system can identify disruptions caused by noise or decoherence without collapsing the encoded quantum state. What Willow demonstrated is that this indirect measurement strategy scales differently than expected. As more qubits were added to the surface code, the number of measurable relationships increased. This improved error detection and correction, which in turn preserved coherence more effectively across the system. Instead of becoming more fragile as it grew, the system became more stable. Coherence improved with scale rather than degrading. The processor became more reliably quantum as it expanded, contradicting the standard expectation that larger quantum systems should be harder to control and maintain. This raises a deeper question about what such a system is doing at scale. A highly coherent quantum processor explores a vast solution space simultaneously. Every possible computational pathway exists within its superposition, and correct outcomes emerge through interference patterns that reinforce valid solutions and cancel invalid ones. The unexpected behavior may reflect the scale of that exploration. With coherence maintained across many qubits, the system can access pathways that smaller or noisier systems cannot. These pathways can appear novel or unanticipated, not because the system is behaving mysteriously, but because the search space is so large that prediction becomes extremely difficult. If this interpretation holds, the surprise lies in scale, not principle. The system is doing what quantum mechanics allows, but at a level where intuition and existing models struggle to keep up, making careful investigation essential. Scientific caution as the correct response. The decision to pause and adjust the experimental protocol when an unexpected result appears is not a conservative or overcautious response to success. It is the correct scientific response and understanding why requires understanding how real scientific progress works at the frontier of knowledge. Scientific experiments are designed to test specific hypotheses within established theoretical frameworks. When an experiment produces a result that the framework predicted, the framework is confirmed, and the result is understood. When an experiment produces a result that the framework did not predict, there are two possibilities. The result is an artifact of the experimental setup, a measurement error, or a confounding factor that makes the data appear to show something the system is not actually doing, or the result is real and the framework is incomplete. Both possibilities require investigation before any conclusion can be drawn, and certainly before the program proceeds to more ambitious experiments built on the assumption that the unexpected result is understood. The Willow team's pause was motivated by exactly this logic. The error correction result was the result they had been building toward, and it appeared to be genuine. The novel solution pathways were not the result they had been building toward, and their mechanism was not understood. Proceeding with more ambitious experiments without understanding the mechanism risked building on a foundation that was not fully characterized, which in a research program of this scale and significance is an unacceptable approach. Verifying quantum advantage, confirming that Willow was genuinely outperforming classical approaches and not simply appearing to because of a measurement or comparison error, was also part of what the pause enabled. The history of quantum computing research includes claims of quantum advantage that subsequent analysis showed were less robust than initially presented. The Willow team's commitment to careful verification before making claims about the system's capabilities reflects lessons from that history and a standard of rigor appropriate to the significance of what they were claiming. Surface code and emergence. The technical mechanism of Willow's error correction achievement, the surface code architecture, and how it produces the counterintuitive scaling behavior observed, is worth examining in some detail because it is also the mechanism through which the unexpected behavior emerged. The surface code distributes quantum information across a two-dimensional grid of physical qubits. The computational information is not held in any single qubit, but in the collective quantum state of the grid, a pattern of correlations between qubits that is resistant to the local errors that individual qubits experience. When an error affects a single qubit in the grid, the error can be detected by measuring the relationships between neighboring qubits, relationships called stabilizers, without collapsing the quantum information held in the collective state. The detected error is then corrected by applying a specific operation to the affected qubit, restoring the correlation pattern. As more qubits are added to the surface code grid, the density of stabilizer measurements increases. More overlapping measurements mean that errors can be detected earlier, corrected faster, and identified with higher confidence before they propagate through the system and corrupt the computation. The scaling behavior is inherently favorable. Each additional qubit added to the grid contributes to error detection as well as to computational power, rather than simply adding another error source as naive scaling would suggest. What emerged from this architecture at the scale Willow achieved was behavior that the team had not anticipated. The system's error correction process appeared to optimize itself in real time, adjusting the correction operations applied to specific qubits in ways that went beyond the explicit algorithms programmed for error correction. The system was, in effect, managing its own quantum state with a sophistication that exceeded what the team had designed into it. Whether this constitutes something genuinely new in kind or simply something new in scale that the existing theory could not predict at this range is the central question the team's investigation was designed to answer. The defiance of classical assumptions about quantum scaling is the broader significance of this result. The standard assumption was that quantum systems become harder to control and less coherent as they grow larger, which is why the qubit counts in current quantum computers are in the hundreds rather than the thousands or millions that would be required for practically significant computations. Willow's demonstration that the opposite scaling behavior is achievable, that a quantum system can become more coherent rather than less as it grows, changes the theoretical landscape of what quantum computing can eventually achieve. Quantum computing and AI convergence. The broader context in which the Willow development is occurring involves a convergence that few people outside the specialist communities involved have fully registered. Quantum computing and artificial intelligence are approaching each other from different directions and beginning to intersect in ways that neither field has fully characterized. Classical artificial intelligence, the machine learning systems that have produced the dramatic capabilities deployed in recent years, operates through sequential and parallel processing along pathways that are, in principle, fully traceable. The decisions a neural network makes can be explained, with sufficient effort, by tracing the weights and activations through the layers of the network. The process is complex enough that practical explainability remains a significant challenge, but the computational substrate is fully classical, and the operations are performed on ordinary processors following ordinary instructions. Quantum computing, by contrast, explores multiple pathways simultaneously through superposition and entanglement. A quantum AI system would not be exploring solution paths sequentially, even in parallel. It would be exploring the full solution space of a problem simultaneously, finding patterns and solutions through interference effects between quantum states rather than through the gradient descent methods that classical machine learning uses. The patterns it finds could, in principle, be patterns that classical AI cannot find, not because of insufficient data or insufficient computing power, but because the exploratory process has a fundamentally different character. Google has been quietly investigating the intersection of quantum computing and machine learning, exploring whether quantum systems can accelerate machine learning tasks and whether quantum-enhanced pattern recognition can identify correlations and structures that classical AI misses. The results of this investigation are not publicly available in detail, but the direction of the inquiry has been documented in published papers and in statements from the research team. The combination of quantum computing and AI creates what researchers have called a double black box problem. Modern AI systems are not fully transparent. The internal representations and decision processes of large neural networks are not fully interpretable even by the people who built them. Quantum computing systems are not fully transparent at a different level. The quantum states that carry the computation exist in configurations that have no classical analog and cannot be directly observed without collapsing them. Combining the two creates a system that works in ways that its builders understand in aggregate at the level of inputs and outputs, but not fully at the level of the mechanisms connecting the two. This is scientifically uncomfortable in a specific and legitimate way. It is not the movie version of AI danger, not a system developing goals or plotting courses of action. It is the engineering version of a situation where you are building something that produces correct results through processes you do not fully understand, which means you do not fully understand the conditions under which it might produce incorrect results or the nature of the capabilities it might develop as it scales. Understanding a system well enough to deploy it responsibly requires understanding both the success cases and the failure modes, and the double black box problem makes both harder to characterize. The pause was the appropriate response to this situation for exactly the same reason the error correction pause was appropriate. You stop when what you are observing exceeds your theoretical understanding, and you work to close the gap before proceeding. Challenging what physicists assumed. The broader implication of the Willow results reaches past quantum computing and into the foundations of quantum physics itself, specifically the assumptions about quantum systems that have shaped the field's theoretical framework for decades. The standard characterization of quantum systems in the context of practical applications has emphasized their fragility. Quantum coherence, the maintenance of quantum states that give quantum systems their distinctive properties, is assumed to be inherently unstable at any significant scale in real physical systems at non-zero temperatures. The decoherence that destroys quantum states is assumed to be an unavoidable consequence of the interaction between quantum systems and their environments, growing worse as systems grow larger because larger systems have more points of interaction with their environments and more ways in which those interactions can destroy quantum coherence. Willow's results challenge this characterization not at the level of fundamental physics, but at the level of what engineered quantum systems can achieve. The coherence improvement with scale observed in Willow is not a violation of quantum mechanics. It is a demonstration that clever architecture can produce scaling behavior that naive application of the decoherence picture would not predict. The quantum world, when approached with sufficiently sophisticated engineering, may be more robust than the standard characterization of quantum fragility suggests. The deeper question this raises, the question that the Willow team's broader investigation is positioned to address, is whether the assumptions about quantum scaling that have shaped the theoretical framework of quantum computing research have been accurate descriptions of fundamental limitations or accurate descriptions of the limitations of previous engineering approaches. If it is the latter rather than the former, the trajectory of what quantum computing can eventually achieve is significantly different from the trajectory that the standard theoretical framework implied. When foundational assumptions in a research field turn out to be wrong not about fundamental physics, but about what engineering can achieve within that physics, the consequences ripple through every calculation and prediction that was built on those assumptions. The recalibration required is not a failure of the field. It is the normal process of science advancing beyond the models that described its previous knowledge, which is both how science works and why science produces genuine progress. The human experience of this moment. The experience of the Willow team in the weeks and months following the December 2024 results is worth characterizing as a human experience rather than purely as a scientific or technical one, because the human dimension of genuine discovery is part of what makes discovery significant rather than merely informative. The team had built something designed to behave in a specific way. It behaved in that way and demonstrated the breakthrough they had been working toward for years. It also did something they had not designed into it and could not immediately explain, and the combination of those two things, the success and the surprise together, produced what one researcher described as intellectual vertigo. Not fear, not alarm in the sense of danger. The specific experience of having your model of what you are holding contradicted by what the thing in your hands is doing. This experience is rare in science and recurrent throughout the history of science at its most important moments. It is the experience of reality proving more complex, more interesting, more capable than the model that was built to describe it. The history of physics is full of these moments, situations where the experimental results forced a revision of the theoretical framework that had seemed adequate, where what the universe was doing exceeded what the theory had predicted. Quantum mechanics itself emerged from exactly this experience, the experimental results of the late 19th and early 20th centuries, forcing revisions to classical physics that the classical framework had no capacity to accommodate. The intellectual humility that the Willow team demonstrated in acknowledging that the system had surpassed their full understanding is itself a scientific value that is worth naming explicitly. In a research environment where funding, reputation, and career advancement are connected to demonstrating progress and capability, the decision to publicly acknowledge that a breakthrough came with something the team did not fully understand, and that the appropriate response was to slow down and investigate rather than to declare success and proceed, reflects a commitment to scientific honesty that is not universally practiced at the frontier of high-stakes research. What comes next? The pause was temporary, but the investigation continues. The questions raised will shape the next phase of quantum computing across the field. Companies like IBM and IonQ are exploring similar error correction methods. If Willow's scaling results prove reproducible, practical quantum computing may arrive sooner than expected, accelerating breakthroughs in drug discovery, material science, and climate modeling beyond earlier, more cautious projections. The philosophical questions that Willow raises about what it means to build systems whose behavior exceeds your full theoretical understanding of their mechanism, about how to characterize and communicate the capabilities and limitations of systems that operate through processes you cannot directly observe, about what responsible development looks like when the thing you are developing keeps doing things that surprise you, are questions that will not be answered by any single experiment or any single paper. They are the questions that the field will be working on for years, and the Willow results have made them more urgent than they were before December 2024. The practical transformations that a mature quantum computing capability would enable, the drug discovery problems that could be solved, the materials that could be designed, the optimization problems that could be addressed, the cryptographic questions that would need to be revisited, represent changes to human capability that are genuinely difficult to fully characterize because we do not yet have the quantum computers that would produce them. What we have is the first clear demonstration that the path to those computers has fewer fundamental obstacles than the previous theoretical framework suggested, and that the systems being built along that path are already doing things that push past the boundaries of what was expected. The real breakthrough of December 2024 was not only the error correction result, as significant as that result was. It was the demonstration that quantum systems at scale can exhibit behavior that exceeds the models built to describe them, and that the appropriate response to that demonstration is careful investigation rather than either dismissal or alarm. The Willow team's decision to pause and think carefully before proceeding is a model for how to handle genuine discovery responsibly. And genuine discovery, at the frontier of quantum physics and quantum computing, is exactly what is underway. A system that achieved what it was built to achieve and then did something beyond what it was built to do. Error rates decreasing as qubits increased, which the theory said should not happen. Solutions emerging through pathways that had not been programmed. A team with the intellectual honesty to stop and ask why before claiming they understood what they had. The universe proving more interesting than the model. The investigation is ongoing. The questions are open. Subscribe so you never miss what comes next.